So the subject of my presentation is going to be a model of the wave equation with what we call a viscous damping. So this presentation, first I'm going to talk about the model that we're going to use. And then I'm going to talk about, of course, the numerical model. And because in the model that we have two different parameters where we want to explore the influence of each of those parameters. And this is going to be the last part of my presentation. So first, maybe we should talk about why do we need to use such a model with viscous damping instead of using just a model of the wave equation. It's because in the experiment that we're going to look at, oftentimes the structure of the underground is not the same everywhere, meaning that at some point we're going to encounter some fluid saturated mediums. And we know from the physical observations that there is a dependency between the frequency of the wave and the attenuations. And we also observe what we call a phase reversal effects. And those two things, they cannot be explained with the conventional acoustics wave theory. So that's why we're going to investigate the model for two additional terms. So this is the kind of experiment that we're going to take a look at. We are located at the surface of the Earth. We send waves into the underground. At some point, they're going to go through a fluid saturated medium. Some of the waves are going to be transmitted and some are going to be reflected. And that's really those quantities that we want to study. We want to know what happens. So you could model this experiment using the acoustic wave equation. But the thing is, in this model that we have, C, the propagation speed is the only thing that can really characterize the change of medium. So we're going to want to do more than that, and we're going to add two additional terms. So the first one is what we call a diffusive term. So it's the time derivative of u. It's commonly used. It does not change the nature of the wave equation. It only brings damping. And the second one, which is the more special one, is what we call a viscous term. So it's this time the time derivative of the Laplacian of u. So it's the highest order term and it changes the nature of the equation. So the model that we're going to have looks just like this. We have the wave equation and those two additional terms. So as I was saying, the system is no longer hyperbolic because it's no longer the wave equation, but we know from this reference that we have an existent, there is a solution. So one thing that we need to consider as well is the perfectly matched layers. So why do we need perfectly matched layers? In this kind of experiment, we're going to simulate a wave, and at some point it's going to reach the boundary. And if you use the typical boundary conditions like Newman or Dirichlet, then you're going to observe non-physical reflections and you want to get rid of them. So the thing is, we could have used what we call absorbing boundary conditions, but on this model that we use, it has not been explored. So we're going to use perfectly matched layers. We're going to extend the domain by a layer, and when a wave is going to go through that layer, it's going to be to disappear completely. So that's what we're going to do. When we do this, we have a more complex domain, a more complex system. Instead of having a simple equation, we now have four equations because the third one is vector valued. So in this system, you can see that in the first equation, you still have the second order wave equation. And you also have those xi functions. Those are related to the perfectly matched layers. That's why you have them. And the functions phi and psi are really the auxiliary variables that we need to introduce in order to have those PMLs. So really that's what the model looks like. Now, from the discretization, we did P1 in space with a triangle mesh, and in time we use an implicit centered scheme and an implicit centered data scheme. So we use this because we have a result where we know that for this data greater than 1/4, we are unconditional and stable. So that's why mainly we will use that scheme. So the discretization is going to look like this. In blue, this is the discretization in time, and in red it's the implicit scheme. We now have 4 problems to solve. And it has to be performed at each time step sequentially. We have to first solve the first one and then compute U, and so on and so on. So in those 4 systems, there's only the first one that is explicit, so it's not really costly, it's easy to solve. But the 3 other ones, we really have to solve them, and it's costly. So adding PMLs to the formulation, it adds a lot of computational cost as well. So that was the scheme we used. So in order to see if the code was working, we choose to replicate an experiment that has been done in the following reference. So the experiment is really kind of the same as introduced at first. We locate a source at the top of the domain, and it's going to travel through 3 different media that are saturated. So on the left and the right, you have a saturation in oil, and in the middle, you have a saturation in water. So we use those damping parameters that we introduced in order to characterize those mediums. And we are also going to use the decrease of speed. So again, this is from the reference that we used, and this is the result that we can observe. So at the top, we have 3 snapshots for the acoustic model, and at the bottom, it's for the viscous diffusive model. So we see that even for the acoustic model, because we have this decrease in speed, something is happening at the second time step and the third time step. We see that the amplitude is decreased, but we still really have reflections. While on the viscous diffusive model, we can see that we really have one transmission, one wave that is transmitted, and one reflection. So overall, everything is dampened in the viscous diffusive model. And maybe we can see better on the 3D snapshots. We really see that the damping is here, is really much damp. If instead of using just the acoustic model. And we can also look at the seismograph. So seismograph is you fix a point in space and you look at how the wave is going to behave over time. And you see that the red dot is the acoustic model. You see that you have plenty of reflections after the wave is going through the medium, where in blue, the model that we use, it's really damp and you don't have such reflections. So that's a good thing. Now we want to, because those are exactly the results we observed in the paper. So the code was working, it was converging at the expected rates. And now we really wanted to see if, the influence of each of the parameters. So what we did is we set one of them to 0 and try to observe what would happen. So that's what we did. And if we look at the seismograph, there's no difference between this, what we've done, and the acoustic model. So this means that one of the parameters was not really useful at all. So it was quite a surprise because it was from a serious context and we really wanted to know why. And in order to do this, so we use this analysis where we suppose that U was a harmonic wave with this expression yielding this that we call alpha attenuation coefficient. This can actually be computed with the following formula that depends on the damping parameter. So we could look for this value of alpha using the 2 parameters that we have. And once we've done this, we can compare the value and we see that there is a large difference in magnitude. So that really explains why we couldn't see anything, because the magnitude of these coefficients was just too big. So after this, we really wanted to have the good parameters. So we came up with new values from these parameters that respect the order of magnitude. So yeah, it was maybe 10 at the power 7 bigger. And this is the results that we observed. So at the top, this is only the viscous model. So this is the term which is the time derivative of the Laplacian, where at the bottom, it's only the time derivative of the U function. So we're looking at the amplitudes of the waves, and we can clearly see that there are two distinct effects. On the viscous model, you have much more reflections than transmission. And in the diffusive model, you see that globally everything is damped, but you don't see such a good reflection. It's transmitted and damped, but it's not much reflected. So if we look at the seismograph as well, we can observe that we indeed have damping. So in yellow, that's the viscous model. In red dots, that's the acoustic, and in blue, the diffusive. We see that there's damping for each new model we introduced, but we also see what we wanted to, which is the phase reversal effect. You can see that the blue line and the red line and the yellow line are really opposing phase, and that's what we expected from the physics. So yeah, really we were happy about that because this work had been done in a really short time. It was for an internship of 2 months. So it was really good to be able to use FreeFan because we could produce some interesting results in a really short time. Obviously, there are many things that we could have done better in the code with using the parallel module and Langevin things. From the theoretical standpoint, we could have studied really the reflection and transmission coefficients, and it would have helped to have really realistic values from the damping coefficients, because the only things that we've been using came from papers where it was sometimes a bit unclear to what was the physics behind. So yeah, thank you for listening, and if you have any questions.
Question, remark, comment, because you go fast.
The formulas are restricted to rectangular domain, or we can generalize it to.
Yeah, I think we can generalize to any domain. Yeah, there's no problem with that.
Which formula is it? The formula for the damping, the viscous layer, what do you call it? PML.
PML. Probably rectangular. Because it's not. If you are approaching Mundi, you peux faire une image of the.
Oui, mais tu peux pas le faire sur la normale? Peut-être. J'ai posé la question parce qu'effectivement, j'ai jamais vu autre chose que des rectangles. Pour les coups. Oui, c'est une réponse.
Par l'extérieur de ça.
You said that adding the PML make the system more costly to solve. Could you give a rough estimate of the costs, either in terms of memory or in terms of time?
I mean, we don't have numbers for the memory, but let's say, I mean, it's maybe 3 times as costly as to solve the wave equation. I think, yeah, it's maybe 2 times as costly just by adding the PML. So yes, that is. Yes.
And the parameters in the PML that after the wave,
yeah,
do they need to change like smoothly? Like,
yeah, I think they have to be smooth. We really used what has been used before, and yeah, but those are.
So you start at 0 in the boundary.
Exactly, and you just increase smoothly. Yes. Yes, please.
Do you have any real data you could compare the models?
I mean, we wish we had, because like I was saying, we mostly took the parameters from papers, and sometimes really the physics was unclear. So yeah, I mean, we wish we got them, but no, that's from real physical experiments.
in real, in a large scale population.
Yeah, but you could, get data from, I don't know, maybe people who are doing more than one and just compare, so, oh, we found oil at this, depth in the ground, and then compare to the results of, oh, and areas.
Yeah.
Thanks to my model, I was like, yes. I'm pretty sure sometimes it's very much.
Yeah. Great.
But I thought dumping was hard to take into account in the time domain. Like, is it? I mean, does it have difficulties having the dumping count? On the 7?
Yeah, because
The first one, the one that you is pretty easy to handle. The other one, completely changing the nature of the equation. So you have, for example, using implicit methods, there is no longer,
Yes.
but it's given in the time domain. So
Yes,
the motivation is to model low frequency effect, but it's still written in time domain. So you don't understand the physics that way.
it's in physics.